For 3.8 billion years, Earth has been conducting the most extensive research and development experiment in history. The laboratory is the biosphere, the researchers are the forces of evolution, and the prototypes are the millions of species that have survived the rigorous testing of natural selection. Every organism alive today is a masterclass in engineering, chemistry, and design. These are survivors that have effectively solved the hardest problems we face today. Problems of energy efficiency, waste management, locomotion, and structural integrity. For centuries, humanity viewed nature primarily as a warehouse of raw materials, a pantry to be raided for wood, ore, and meat. But a profound shift is occurring in the scientific and industrial worlds. We are no longer just extracting from nature, we are learning from it. We are entering the age of biomimetics, the discipline of decoding nature's best ideas to power our future. This field is not simply about copying the shape of a leaf or the curve of a bird's wing for aesthetic reasons. It is about decoding the deep principles of biological survival and translating them into synthetic technologies. It represents a fundamental clash between two philosophies of engineering. Historically, human industry has been built on a process often described as heat, beat, and treat. We forge steel in massive blast furnaces, we crush rocks to make concrete, and we synthesize chemicals using high pressures and toxic solvents. Our systems are linear. We extract, manufacture, consume, and discard. Nature, conversely, builds at ambient temperatures and pressures. Life uses water as a primary solvent. Most importantly, nature functions on a closed-loop system where waste does not exist. The byproduct of one organism is the feedstock for another. A cherry tree that drops thousands of blossoms is not being wasteful. It is enriching the soil for its own future growth. The promise of biomimetics is to move us from an industrial age defined by brute force to one defined by this kind of elegant efficiency. The most immediate and tangible revolution is happening in materials science. Our current strongest materials, like steel, Kevlar, and carbon fiber, require immense energy to produce. Nature, however, constructs high-performance materials from the bottom up, arranging atoms and molecules into hierarchical structures that still baffle our best engineers. Consider the dragline silk of the golden orb weaver spider. Pound for pound, it is 5 times stronger than steel and tougher than Kevlar. But its true brilliance lies in its duality. It is both strong, meaning it resists breaking, and extensible, meaning it is capable of stretching. Man-made materials usually sacrifice one for the other. Glass is strong but brittle. Rubber is stretchy but weak. Spider silk achieves this balance through a complex arrangement of crystalline protein structures, which provide strength, embedded in a semi-amorphous matrix which provides stretch. For decades, humans tried to farm spiders, but their territorial nature and tendency towards cannibalism made this impossible. Today, biomimetic startups are bypassing the spider entirely. By inserting spider DNA into yeast, bacteria, and even goats, scientists are brewing liquid silk protein in vats, similar to the process of brewing beer. This liquid is then spun into fibers that are being used to create biodegradable running shoes, lightweight ballistic armor, and surgical sutures that dissolve harmlessly into the body. While spider silk revolutionizes structural integrity, other creatures are revolutionizing how we create color. Look at the shimmering blue wings of the morpho butterfly. If you were to grind those wings into a powder, the blue would disappear, revealing a dull brown dust. This is because the blue is not a pigment. It is what we call structural color. The wing is covered in microscopic scales shaped like tiny Christmas trees. These nanostructures interfere with light waves, reflecting only the blue spectrum, while canceling out the rest through destructive interference. Human paints and dyes are often toxic. They fade over time, and they require heavy chemical processing. Biomimetic researchers are now creating films and fabrics with nanostructures that mimic the morpho butterfly. These materials produce brilliant, fade-proof colors without a single drop of dye. Imagine a car paint that never chips or fades because the color is built into the physical structure of the metal itself. Or a screen display that uses a fraction of the power by manipulating ambient light rather than generating its own pixels. Moving from light to motion, we encounter the shark and a discovery that changed fluid dynamics. For years, engineers assumed that to move fast through water, a surface had to be perfectly smooth. Then we looked at the shark. Shark skin is covered in tiny, tooth-like scales called dermal denticles. These denticles are grooved and arranged to channel water efficiently, preventing the formation of turbulent eddies that create drag. This counterintuitive discovery, that a textured surface can be more aerodynamic than a smooth one, has been revolutionary. Riblet films mimicking shark skin have been applied to the hulls of ships and the wings of airplanes, reducing fuel consumption by simply reducing friction. Even competitive swimwear has utilized this technology, aiding swimmers in breaking world records before being regulated for providing too much of an advantage. Furthermore, these denticles serve a second purpose. They are anti-fouling. Bacteria and barnacles struggle to latch onto the shark's rough, shifting skin. This has led to the development of micro-pattern surfaces for hospitals that physically inhibit bacterial growth without the use of antibiotics, a critical tool in the fight against superbugs. As we scale up from materials to entire structures, we find that nature is also the ultimate architect. Our modern buildings are essentially sealed glass boxes fighting against the environment. We pump massive amounts of energy into HVAC systems to cool them down or heat them up. Nature builds structures that regulate their own climate passively. The most famous example of architectural biomimicry is the Eastgate Center in Harare, Zimbabwe. The architect Mick Pierce faced a challenge: build a large office complex without expensive air conditioning. He turned to the mounds of the Macrotermes michaelsini termite. These termites farm a fungus inside their mounds that requires a precise temperature of 87 degrees Fahrenheit, while the outside African savanna fluctuates wildly between 35 and 104 degrees. The mound achieves this stability through a complex system of vents and tunnels. Cold air is drawn in at the base, and as it warms from the metabolism of the termites and the fungus, it rises and exits through the chimney, creating a continuous convective current. The termites constantly adjust the vents to regulate airflow. The Eastgate Center mimics this passive cooling. The building is constructed from materials with high thermal mass, like masonry, which absorb heat during the day and release it at night. A series of fans and vents circulate air through the building's hollow bones, mimicking the termite tunnels. The result is a building that uses 90% less energy for ventilation than a conventional building of its size. In the deep ocean, we find another architectural marvel: the Venus flower basket sponge. This organism withstands immense hydrostatic pressure, yet its skeleton is a delicate-looking glass lattice. When engineers analyzed it, they found a hierarchy of structural reinforcements, diagonal ridges and spiral layers that stop cracks from propagating. This sponge inspired the design of the Gherkin Tower in London. The tower's diagrid structure allows it to be incredibly strong, yet lightweight, requiring less steel than a traditional skyscraper. The spiraling gaps in the floors allow air to flow through the building, reducing the reliance on air conditioning, much like the sponge allows water to flow through it to filter feed. And speaking of buildings, concrete is the second most consumed substance on Earth after water, but it is prone to cracking. When water enters these cracks, it rusts the steel reinforcement, leading to structural failure. Biomimetic material scientists have developed living concrete infused with bacteria strains and starch. When the concrete cracks and water seeps in, the dormant bacteria wake up. They feed on the starch and excrete calcite, effectively limestone, which fills the crack and seals it shut. The concrete heals its own wounds, just like human skin, potentially extending the lifespan of infrastructure by decades. Now, let's look at how we move through these environments. Traditional robots are rigid, jerky, and struggle with uncertain terrain. They are made of metal and motors. Biological organisms are soft, compliant, and incredibly adaptable. This has given birth to soft robotics. Consider the octopus. An octopus has no bones. It can squeeze through a hole the size of its beak, yet it is strong enough to crush a crab. Its arms have infinite degrees of freedom. They can bend, twist, and elongate at any point. Engineers are building soft robotic arms made of silicone and powered by pneumatic fluids. These robots don't need complex joints. They move by inflating chambers within their soft bodies. A soft robotic gripper can pick up an egg, a wrench, or a live mouse with equal ease, simply by conforming its shape to the object. This is revolutionizing warehouse logistics and agricultural harvesting, where rigid robots often crush delicate fruits. It is not just the body of the robot that is being updated, but the brain. In nature, individual ants or bees are simple, but the colony is brilliant. They exhibit swarm intelligence, solving complex routing problems to find food or build hives without a central commander. Roboticists are programming swarms of simple drones that communicate locally with their neighbors. If one drone finds a target, like a survivor in a disaster zone, it signals its neighbors, and the information ripples through the swarm. This allows for robust systems. If one robot fails, the swarm continues. We also see this in the mechanics of movement. The viral videos of Boston Dynamics. Robots show machines that can run, jump, and backflip. These feats are achieved by analyzing the dynamic stability of animals. A cheetah doesn't just use its legs. It uses its tail for balance and its flexible spine to store energy. Biomimetic robots are moving away from static stability, which is standing still without falling, to dynamic stability, which is essentially falling continuously but catching oneself, allowing them to navigate rough terrain that would trap a wheeled vehicle. Energy is another sector where nature is vastly superior. Our energy systems are brute force. We burn dead plants or split atoms. Nature runs entirely on current sunlight. A leaf is a masterpiece of energy conversion. It takes sunlight, water, and carbon dioxide and turns them into sugar and oxygen. The Artificial Leaf Project aims to replicate this. Scientists have developed devices using silicon and catalysts that, when dropped in water and exposed to sunlight, split the water into hydrogen and oxygen. The hydrogen can be stored and used as a clean fuel. More advanced versions are attempting to capture carbon dioxide from the air and convert it into liquid fuels, effectively reversing combustion. If scalable, this technology would not just be carbon neutral, it would be carbon negative. Sometimes, energy efficiency comes from unexpected places, like the humpback whale. Whales are massive, yet they are agile swimmers. Biologists noticed that the leading edge of their pectoral fins is not smooth, but covered in bumpy tubercles. Fluid dynamic simulations revealed that these bumps channel water into rotating vortices, which keep the water attached to the fin at steep angles. This prevents stalling and increases lift. This discovery has been applied to wind turbines. Blades with whale bumps can operate at steeper angles and lower wind speeds, capturing more energy while being quieter. It proves that sometimes, a bumpy ride is more efficient than a smooth one. In the realm of water scarcity, we look to the Namib desert beetle. It survives one of the driest places on Earth by drinking fog. Its back is covered in a pattern of hydrophilic bumps on a hydrophobic background. When fog rolls in, water condenses on the bumps, and when the droplet gets heavy enough, it rolls off the waxy background straight into the beetle's mouth. Engineers have replicated this texture to create fog harvesting nets. In arid regions like Chile and Morocco, these biomimetic nets are pulling thousands of liters of fresh water out of thin air every day. Perhaps the most personal application of biomimicry is in medicine. Modern medicine often involves invasive procedures, but nature offers a gentler touch. No one likes getting a shot, but have you ever felt a mosquito bite you? Often, you don't. The mosquito's proboscis is not a single needle, but a fascicle of several jagged, vibrating stylets. It saws through the skin with minimal force. Japanese engineers modeled a hypodermic needle on this mechanism. It is conical and works via a subtle vibration, reducing the contact area with nerves and gliding into the tissue with significantly less pain. For internal injuries, researchers sought a glue that could work in the wet, bloody environment of the body. They found the dusky Arion slug. The defensive slime of this slug is incredibly sticky and elastic. By analyzing the proteins in the slime, scientists created a hydrogel adhesive that binds to wet tissues and can stretch with the beating of a heart without breaking, potentially replacing sutures in complex surgeries. Even the storage of medicine is being reimagined. Vaccines usually require a cold chain of constant refrigeration. In developing nations, the lack of electricity often breaks this chain. Enter the tardigrade, or water bear. These microscopic creatures can survive being dried out, frozen, boiled, and even irradiated. They do this by replacing the water in their cells with a sugar called trehalose, which turns into a protective glass, preserving their internal structures. Biochemists are using this zero-preservation technique to dry stabilize vaccines. Wrapped in a microscopic sugar glass, these vaccines can be stored at room temperature for months. To use them, you simply add water. Finally, we look at the very tool we use to process all this information, the computer. Our computers use the von Neumann architecture, separating memory and processing units. This is fast, but energy-hungry. The human brain, however, integrates memory and processing in the synapse. It is slow, but massively parallel and incredibly efficient, running on the energy equivalent of a dim light bulb. Scientists are building neuromorphic chips that mimic the physical structure of the brain. These chips use spiking neural networks. Instead of a constant flow of electricity, they send discrete spikes of information only when needed, just like neurons firing. These are exceptionally good at pattern recognition and sensory processing for robots. And for storage, we look to DNA. We are generating data faster than we can build hard drives. Nature has stored the blueprint of life in DNA for billions of years. DNA is incredibly dense. All the data in the world could fit in a teaspoon of DNA. Researchers are now encoding digital files into synthetic strands of DNA. It is the ultimate archival storage. Kept cold and dry, it can last for hundreds of thousands of years. Despite the immense potential, biomimetics is hard. Nature is complex. A spider spins silk using a process that involves pH gradients and protein alignment within a microscopic duct. Replicating that in a factory is an engineering nightmare. Furthermore, nature designs for resilience, while humans design for efficiency. A bone is heavier than it needs to be to withstand walking because it is designed to survive a fall. Human engineering often strips away redundancy to save cost, making our systems brittle. Adopting biomimicry requires a shift in mindset, valuing longevity and adaptability over short-term profit. There is also the risk of greenwashing. Just because a shape looks like nature doesn't mean it is sustainable. A plastic chair shaped like a leaf is still a plastic chair. True biomimicry emulates not just the form, but the process and the ecosystem. We are standing on the precipice of a biohybrid future. The division between the born and the made is blurring. We will live in buildings that breathe, drive cars that heal their own scratches, wear clothes that harvest energy from our movement, and compute with machines that think like brains. Biomimetics is more than a technological trend. It is a humbling correction to human hubris. It acknowledges that we are not the first inventors. We are the youngest apprentices in a workshop that has been operating for eons. The blueprints are all around us, in the forest floor, the coral reef, and the spider's web. All we have to do is quiet our machines long enough to listen, observe, and learn. The future of technology has been here all along,